In the last lecture, we've seen that okay, we have any finite extension of the field F with characteristic 0 is the simple extension. Okay, so here we prove that the K is the finite extension of F with characteristic 0, then K is the simple extension of that field F. Okay, so today we will see first some definitions. Okay, some new points are there: separable element, separable extension, and perfect fit. These are the three definitions are there. Okay, so look at the first definition: separable element. What is separable element? Separable element. Okay, get it. An element, an element A. Okay, in an extension, capital K of a field of a field capital F. Okay, it's called separable over F. Separable over capital F. If it satisfies, if it satisfies a polynomial, a polynomial over F, over capital F with F, having no multiple roots. Okay, what is the definition of separable element? An element A in an extension K of the field F. If this element A satisfies the polynomial over the field F having no multiple roots. For example, if suppose this one is Q, okay, this is your F, and Q is the R is the extension of what? Q. Okay, take A is equal to root 2. Okay, so what is the extension of Q is here? Q root 2. Okay, not R. Wait a minute. Hello, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Take this. K is equal to root 2. Q root 2. K is equal to Q root 2. So here the Q root 2 is an extension of Q. Okay, take A be the element root 2. So this root 2 satisfies the polynomial. Which one this implies? Take x is equal to root 2. So we have x square is equal to 2. So this implies x square minus 2 is equal to 0. So here the x is equal to root 2. Okay, or a is equal to root 2. Satisfies the polynomial. Which polynomial? X square minus 2.
X square minus 2.
Okay, having no multiple roots. No multiple roots. What are the roots of this one? X square minus 2. So here the two roots of this polynomial. Which one?
Plus minus root.
Plus minus root. Okay. So for this polynomial, we have no multiple root. So this implies A is equal to root 2 or x is equal to root 2 is and separable is a separable element. Okay. Separable element over the field Q. Okay, any doubt?
No, sir.
No. So example number two, x is equal to, suppose we take here I. So this element I satisfies the polynomial x square plus 1 is equal to 0. Okay, on P of x. This belongs to R of x. Sorry, R of x. Correct. This polynomial belongs to R of x. So here the k is equal to complex number c and f is equal to what? Set of the. So here x is equal to r is
R.
separable over r. Why? Because this x square minus 1 satisfies the polynomial I with no multiple. Okay. Any doubt in the definition? Now, the next example,
No, sir.
next definition is separable expansion. So, extension K and extension Q of a field of a field capital F. It's called separable. An extension K of the field F is called separable extension. Okay, or separable over F if each element each element of capital K is separable over F. Separable over F. Suppose this one is the field F and this is the extension of, then every element of the field K is separable over F. That means every element of K satisfies the polynomial over F having no multiple roots. Then we can say that this K is the separable extension of the field F. Okay, any doubt? Every element of K
No, sir.
कोणताही एक एलिमेंट घेतला त्यातला K मधून तर तो काय पॉलिनॉमियल सॅटिस्फाय करायला पाहिजे ओव्हर F वर having no multiple roots. Okay, now wait a minute. Wait a minute. Wait a minute. Wait a minute. एकच मिनिट बघ. hang झालं. Wait a minute. Okay. Is it screen visible at all? Now the next definition is separable
Yes,
extension.
sir.
Separable extension. Once again, look at it. Right. What is separable extension? Separable extension. Okay. An extension K of a field of a field capital F. It's called separable over F or separable extension of F. Separable extension of capital F if each element of K is separable over F capital. Okay, any doubt in this definition? Okay, now the next definition is
No, sir.
perfect field. What is perfect? Neat, let's study the definition today. Okay. What is perfect field? A field F is called perfect. It's called perfect field. Field F is called perfect if all the extension, all the finite extension of capital F are separable extension. Okay, all the finite extension of capital F are separable extension. Then F is called as perfect field. For example, Q. Okay, field of rational number. Q root 2 is the finite extension of what? Q. So here Q of
Q.
root 2. So take any finite extension of this field, we get separable extension. Q root 2, Q root 2, root 3. Okay. Suppose this one is the field Q. Suppose this one is Q root 2. So this one finite extension of what? Degree of Q root over Q is 2. So this is the finite extension. So every element of Q root 2 satisfies the polynomial having no multiple roots over the Q. This one is Q root 2 root 3. This one is also what? All the finite extension of Q are here separable extension. Okay. Now we have one theorem. If the field of characteristic 0, then the field is perfect. Okay, what is the next theorem? Any field with characteristic 0 is perfect field. Okay, so what we have to do here, the field is perfect. That means every simple extension, every finite extension of F are separable extension. Okay, look at the theorem. This theorem. Next theorem is a field of characteristic 0. Field of characteristic 0, then is perfect. कोणत्याही फील्डची characteristic 0 असेल तर every simple extension must be a separable extension. That means if A belongs to K, then A satisfies the polynomial having no multiple roots. Okay, perfect field definition क्या है? Every finite extension is separable extension. What is separable extension? Each element belongs to K satisfies the polynomial over F having no multiple roots. Okay, so दोनों definition ही perfect है, almost perfect, तुम्हारा proof करते हैं. Proof. Let capital F be a field of characteristic 0. Be a field of characteristic 0. What we have to do here? F is the perfect field. That is, every extension of F is a separable extension. Every finite extension. Sorry. Finite extension. Every finite extension of F is separable extension. What is separable extension? Every element belongs to that extension K satisfies the polynomial over F having no multiple root. Okay, so here let us assume F be a field of characteristic 0. And we know that the field F will be perfect by the definition. Okay, perfect if every finite extension of capital F is separable. Okay, and every the field F will be perfect if every finite extension of B is separable over capital F. Okay, so here we have to take any finite extension, arbitrary finite extension of F. Okay, and if that extension is a separable extension, then the field F is perfect. Okay, for this one, we here assume let K, capital K, be any, okay, arbitrary, okay, any finite extension of capital F. Okay, if we prove this extension, this finite extension is separable extension, then F is perfect.
Separable.
Okay, any doubt up in here? Okay. If
No, sir.
K is the finite extension of F, we know that every finite extension is what? Algebraic extension. Okay. K
Algebraic extension.
algebraic extension. Okay, well done. Now we have to prove that this capital K is separable over F. That is separable extension of F. Okay. What is the theory to prove this K is the separable over F? Okay, so what we have to do here? K is separable over F. That is, every element belongs to K satisfies the polynomial over F having no multiple. Okay. Now take any element A belongs to K. Okay, A belongs to K. B any arbitrary element. Okay, and what we have? K is the finite extension of F. That means degree of K over F is what? Let's say this one is N, finite extension. Okay, and K be the any element from A be the any element from the field K. and degree of k over f is what? N. So this implies A satisfies the polynomial. A, every finite extension is algebraic extension. Okay. So by the definition of algebraic extension, any element from the K satisfies the polynomial f of x, small f of x, belongs to capital F of x of degree at most n. Okay,
N.
at most n. Okay, A belongs to what here? Q. What is the value of A? 1. So what is the polynomial? Minimal polynomial for A is x minus 1. Okay, this is P of x. And what is the degree of P of x here?
X
At
minus 1.
most n. Okay, at most 2.
1.
I don't know that is A is root 2 or 1. Okay, this is the arbitrary element. So here A satisfies the polynomial f of x belongs to capital F of x of degree at most n. Okay, so this implies f of A is equal to 0. Okay, now in the last semester we've shown that if f is the field, then f of x is unique factorization domain. Okay, so by the unique factorization theorem, unique factorization theorem for polynomial, okay, over a field f. What is that theorem? First, write if f is field, if f is field, this implies what? F of x is unique factorization domain. Okay, so by the unique factorization
UFD.
domain for the polynomial over the field f, this f of x belongs to what here? Capital F of x can be expressed product of irreducible, okay, element expressed. This f of x can be expressed as f of x is equal to q1 of x, q2 of x, up to so on qm of x. Okay, this f of x is unique factorization domain. Okay, and this f of x we can write in the form of product of irreducible elements belongs to capital F of x, where q1 of x, q2 of x, up to so on qm of x are the elements belongs to capital F of x. Okay, and they are what irreducible. They are irreducible. Okay, now we have what we have f of a is equal to 0 because f satisfies the polynomial a. Okay, f of a is equal to 0. So this implies q1 of a into q2 of a into q3 of a up to so on qm of a is equal to 0. Okay, if the product of this all this is equal to 0, this implies qi of a is equal to 0 for at least 1 I. Is it correct? Between
Yes, sir.
either in between 1 and 9. What is the reason for this one? Correct is not correct. And the whole 0 है. They at least एक reason हो सकता है. Why? नहीं, कैसा होगा?
Zero polynomial येते sir.
Of 2 elements is equal to 0. Either one of them
Irreducible either one of
either one of them is 0 असायला हवा. पण इथे काय
0.
2 is equal to 0 inside 6. Okay. But here one of them is 0. But here what is the reason for this? Algebra मध्ये आपल्याला reason हो ना. Because f is the field. F of x is what? Integral. Okay. Any doubt now?
Yes, sir.
Okay. So here a satisfies.
No, sir.
Reason काय आहे? What 0 असेल तर at least one of them 0 आहे माहिती आहे. पण याला reason काय algebra मध्ये आपल्याला f of x is an integral. Okay, without 0 divisor. Integral आहे काय? 0 divisor आहे. Okay. So this implies a satisfies and irreducible polynomial. Which one? Qi of x belongs to capital F of x. So by previous term, a satisfies the polynomial. By previous term, what we have? Qi of x it satisfies a and it is what? Irreducible. Okay. Over f with characteristic 0. So what it implies? Qi of x having
F of A
no
is
multiple roots. Friday क्या दिया Friday. To field f with characteristic 0 and if Qi of x is irreducible, then that polynomial having no multiple roots. Okay, if the characteristic of f is p, which is not equal to 0, then Qi of x is in the form of f of x is in the form of g of x raised to p. Okay, so here Qi of x having no multiple roots. So this implies a satisfies a polynomial over f having no multiple roots. Okay, so this implies what is the definition of separable over there? So A is separable extension of f, that is separable over f. If K is what? Any arbitrary field, any arbitrary extension of f is not separable extension. Okay, but K over f is what? Finite extension. So this implies hence capital F is a perfect fit. Any doubt? Okay, एकदा field perfect दाखवायचा असेल तर
no,
त्याला
sir.
आपल्याला any extension, any finite extension of the field is a separable extension. What is separable extension? Every element from that extension will A satisfying the polynomial having no multiple roots. Okay. Any doubt in this theorem? चलिए अपन त्याच्यानंतर काय म्हणणार? Period of
No, sir.
characteristic 0 is perfect. तुम्हाला एक्झाम्पल काय होती? field is a field having option which of the following is perfect field? ZP, ZP square, okay, ZP2, and field of rational number. Future. Okay. Now, the next theorem is, or we can say that example is, what is the statement? Prove that any finite extension, any finite extension of perfect field of perfect field is perfect. Any finite extension of a perfect field is perfect. Suppose this F is in perfect field. So extension, any extension of this field. Suppose this is the K. This is the finite extension. That is K over F is what? Degree of K over F is finite. That is N. Then this K also be a perfect. Okay. जर हा K जर perfect दाखवायचा असेल तर काय करावं लागेल? Any extension of K, that is suppose this one is here, is what? Separable. Any arbitrary extension. Okay, is it correct? Okay, any finite extension of K
Yes, sir.
is separable, then K is perfect. Okay, what we have in the statement? Any finite extension of the perfect field. Suppose this F is perfect and K over F, the degree of K over F is finite, that is N. Okay, then K is perfect. So we have to prove that K is perfect. That means every extension, every finite extension of every arbitrary extension of K is the separable extension. Okay, जर हा तुमचा L हा separable extension of K झाला तर K perfect होईल. Okay. Look at the proof. Let capital F be a perfect field. A perfect field. And capital K be any finite extension of F. Finite extension of capital F. Okay, now let L be any finite extension of K. This one is F, which is a perfect field. Okay, that means every extension of F is a separable extension. Okay, and what is given to us? Any finite extension of the perfect field. So the degree of K over N is what? The degree of K over F, sorry, is equal to N. Okay, and this one K is separable over F. Why? Because F is perfect. We have to show that this K is the perfect field. But by the definition of perfect field, we have to show that this K is in every extension of K. So suppose this is the extension of K. It's separable. Okay. This L is fine. We have to show that this K is what? Perfect field. That means by the definition of perfect field, all the finite extension of K are what? Separable. Okay, so here we taken as L is the finite extension of K. If suppose this L is the separable, then K is the perfect field. Okay, so that's why we have assumed L be a the finite extension of K. Any doubt? Okay. Now look at that. So
No,
this
sir.
implies degree of K over F is what? Finite. Okay. Also, the
Finite.
degree of L over K is what? Again, finite. Okay.
Finite.
By the transitivity. It's already given a vocabulary. By the transitivity of finite extension. L over F is
L over
finite.
F is finite.
Transitivity of finite extension. By transitivity of finite extension, we have what we have, the degree of L over F is equal to degree of L over K into degree of L. What is L over K is finite. Okay, so this implies, so as F is what? What is given to us? F is perfect. F is the perfect field. Hmm. By the previous theorem, every finite extension of F is what? Separable. Every finite extension of, look at here, as F is the what? Perfect field. So by the definition of what? Perfect field, every finite extension, all the finite extension of,
Hello, am I audible? Hello,
Yes, sir.
wait a minute.
Sir, your voice is low.
Now, okay. Now look at here. What is the definition of perfect field? If we a F be a perfect field, if every extension, all the extension of F are separable extension. Okay. Now look at here. The degree of L over F is what here? Finite extension. Finite. So as F is the perfect field and degree of L over F is finite. Okay, so by the definition of perfect field, every finite extension of F, every finite extension of the field F, capital F, is separable over F,
Separate.
separable over F, and hence L is what? L is separable
Separate.
over F. Okay, that is every element A belongs to capital L satisfies the polynomial, satisfies a polynomial over F. Okay, over F having no multiple roots, no multiple roots. Okay, any doubt up to here?
No, sir.
Now, in particular, suppose this A belongs to L, satisfies a polynomial over K, which is the superfield of F. Okay, हा A काय करतोय? Polynomial satisfy करतोय over F, but F is contained in K. तेच दिलंय ते. Okay, so here A satisfies the polynomial over now K. Okay, over F आहे म्हणजे काय? तो F कशात contained आहे? K मध्ये. So here over K is satisfies the polynomial having no multiple root. Having no multiple roots. Okay, so that is every element A belongs to K is separable over F. Okay, A belongs to capital L is separable element over K. Okay, A is the arbitrary element. So thus, what we get? Every finite extension L of K. Here we prove that every finite extension of L of capital K is separable. Is over K. Okay, so this shows that this shows that this shows that K is perfect field. Perfect field. Okay, so hence every finite extension, every finite extension of a perfect field, of a perfect field is what? Perfect.
Perfect.
Okay, any doubt?
No,
No,
sir.
sir.
Okay, so this is the end of our second chapter, splitting field. First chapter is what? Extension field. Na? Okay,
Field extension.
now we are going to we are going to take the third chapter, Galois theory. Okay, the Galois is the scientist who gave this theory. What he says that the group of atomorphism. Okay, what is the atomorphism? An isomorphism with same domain and codomain.
Codomain.
ओके, एखाद्या फंक्शनचा जर डोमेन आणि कोडोमेन सोबत एकच असेल तर त्या आयसोमॉर्फिझमला काय म्हणतो आपण? ॲटोमॉर्फिझम. ओके, इफ दी F is the field, he says that F is the field and the set of all the atomorphism on that field forms a group. Okay, set of all the atomorphisms of a field, त्या फील्डवर कोणकोणते ॲटोमॉर्फिझम डिफाईन होतात त्याचा कलेक्शन केल्यानंतर तो कलेक्शन काय करतोय? ग्रुप फॉर्म करतोय विथ बायनरी ऑपरेशन इज composition of that two function. Okay, for example, before going to the see some definitions, first we define the atomorphism on the set of rational number. What is atomorphism? Look at here. Atomorphism. Now look at here. Anyone knows that how many atomorphisms are exist on the field of rational number? Okay, and the set of all the atomorphisms on the field Q we denoted by A of Q. Okay, this is the collection of all the atomorphisms F, such that F is atomorphism on Q. Okay, collection of all the atomorphism on Q. Anyone knows how many atomorphisms are defined on the field Q? Okay, look at here. Only one atomorphism. Okay, if suppose mm, that f is the function from the field is q to q. Okay, here we study the atomorphism. Hence, the domain and codomain is must be same. Okay, and that atomorphism must be an identity element, identity function. I of x is equal to x. That is f is equal to I is equal to I of x is equal to x. Then this I is the only atomorphism on the Q. ओके, दूसरा काय एक्झिस्ट होत नाहीये. तर पहा, if suppose this one is the function, okay, suppose this one is phi is the function, okay, from the set of rational number to set of rational number defined by q of x is equal to x, then phi is the only atomorphism on the field q. Okay, on the field q. Okay, if suppose phi 1, suppose this one is suppose let, why we cannot take the other than this mapping, such that that phi 1, that phi, that function, that mapping is an not the atomorphism. Why? Suppose look at here, phi 1, let phi 1 be any other atomorphism, be other any any other atomorphism on the field q. Okay, any other atomorphism on the field q. So look at here, the set of all the atomorphism we denoted by a of q. Okay, so this phi 1 suppose belongs to a of q, na, a of q, set of all the atomorphism from on q. Now let any element from this set q is in the form of p by q, because q is the set of rational number. Let p by q belongs to set of rational number. Okay, so therefore p divided by q we can write in the form of 1 plus 1 plus 1 plus up to how many times? P times. Okay, now 1 plus 1 plus 1 plus up to how many times? Q times. Okay, and apply now phi 1 on the both sides. So here the phi 1 of p divided by q is equal to phi of, okay, this element as it is, phi 1 of. Now phi 1 of p divided by q is equal to phi of 1, phi 1 of 1, sorry, phi 1 of 1 up to how many times? P times. Why? Because phi 1 is an automorphism. That means it is an isomorphism divided by phi 1 of 1 plus phi 1 of 1 plus up to so on q times. Since here the phi 1 is an atomorphism, so what is the phi 1 of 1?
1.
Identity maps to identity. Okay, end of the isomorphism. So here phi 1 of p by q is equal to, what is this one? 1 plus 1 plus up to so on. हा कशात जाणार तुमचा? कोडोमेन मध्ये. पण कोडोमेन काय तुमचा? Q itself. Okay, Q itself. So here the identity element 1 is the identity. हा 1 कुठून येतोय? हा डोमेन मधून येतोय. आणि जो काय इमेज आहे याचा phi 1 of 1 that belongs to Q. So here by the isomorphism, this identity maps to identity of this codomain. But what is the identity of this codomain? Again it 1. So here 1 plus 1 plus 1 up to how many times? P times divided by, similarly 1 plus 1 plus up to so on, this up to q times. Okay, so here we get phi 1 of P divided by Q is equal to what? P divided
P
by.
by Q.
So only identity mapping is defined. Okay, is an isomorphism. Okay, or atomorphism on the set of rational number. Okay, so I is the only mapping from the set of rational number to set of rational number. ओके, म्हणजेच कोणताही जर एखादा आयडेंटिटी मॅपिंग असेल तर त्याला आपल्याला आयसोमॉर्फिझम दाखवण्याची गरज नाहीये, तो ऑटोमॅटिकली आयसोमॉर्फिझम असतोच आधीपासून. ओके, नाउ सिमिलरली on set of real number, on the set of real number we can define only one atomorphisms. Atomorphism, which one? That's identity itself. R to R is the only mapping such that this I is an atomorphism. I of x is equal to x, for all x belongs to what? R. ओके, दुसरा असा एक मॅपिंग मला एक्झिस्ट करून दाखवा की तो ॲटोमॉर्फिझम असेल. एक्झिस्ट होतच नाहीये, फक्त आयडेंटिटी मॅपिंग हा एकच मॅपिंग आहे तो जो आयसोमॉर्फिझम होता. ओके, नाउ if the field is complex number, if the field is set of complex number, then how many atomorphisms we can define on the set of complex number? Phi 1 of C to C. Since phi 1 is an atomorphism, the domain and codomain must be same, such that phi 1 of A plus IB is equal to A plus IB. This one is the mapping such that phi 1 is an isomorphism. And also one more mapping is there, phi 2, such that A plus IB maps to
A minus.
A IB, complex conjugate. These are the two mappings on the set of complex number such that this phi 1 and phi 2 must be an automorphism. Okay, for all A plus IB belongs to set of complex number. ओके, म्हणजेच हा काय असेल, 1 1 पण आहे. आयडेंटिटी मॅपिंग तर 1 1 ऑन 2 असतोच आधीपासून असतो. ओके, तो दाखवण्याची गरजच नाही. आणि होमोमॉर्फिझम पण असतो. ओके, तुमचा डोमेन आणि कोडोमेन सोम असल्यामुळे तुमचा हाच मॅपिंग इथे येतोय. त्यामुळे इथे कोडोमेन मध्ये जर होमोमॉर्फिझम असेल तर इकडे now if suppose the field is q of root 2 or root 3 root 5, if our field is q root 3 root 5, then how many atomorphisms we can define? What is the nature of this set? Is A plus B root 3 plus C root 5 plus D root 3 root 5. Okay, such that E, B, C and D are the elements from Q. Okay, if suppose F is equal to Q root 3 root 5, then how many atomorphisms we can define on this field? One mapping is, look at here, this root 3 root 5. Okay, तुमचा इथे काय field Q root 3 root 5 आणि mapping from this one is also codomain is root 3 root 5. This mapping, first one, identity mapping, this root 3 root 5 maps to root 3 root 5. Okay, this is F1. And what is F2? Root 3 root 5 is maps to minus root 3 minus or plus root 5. Okay, this one is F2. This mapping is also what? Automorphism. F3 root 3 root 5 is maps to root 3 minus root 5. And F4, the mapping root 3 root 5 maps to minus root 3 minus root 5. These are the four mappings exist on this field such that this f1, f2, f3 and f4 are the atomorphism. ह्याचा अर्थ काय रूट 3 रूट 5 कळते का काही?
Yes, sir.
पहा जर नाही समजत असेल तर f1 of look at here f1 of a plus b root 3 plus c root 5 plus d root 3 root 5 हा कसा डिफाइन होईल? This elements maps to identity mapping, that is b root 3 plus c root 5 plus d root 3 root 5. Okay, हा तुमचा आयडेंटिटी मॅपिंग. सेकंड वन a minus 3 plus है ना इथे a minus b root 3 plus c root 5. This one is f2. Okay, plus minus root 3 म्हणजे इथे काही मायनस. ओके, minus d root 3 root 5. Okay, similarly आता इथे काय येईल? इथे मायनस येईल. Okay, and all is as it is. Okay, and fourth one is इकडे मायनस इकडे काही प्लस. Any doubt?
No, sir.
These
Sir.
are the four mappings such that 1 1 onto an isomorphism. That is, we can define these four mappings on the field of q root 3 root 5 such that mappings are isomorphism. Hence, this set of all the atomorphisms on q root 3 root 5. What are this one? F1, F2, F3 and F4. And these four functions with composition forms a group. Okay, the set of all the collection of the atomorphism, set of all the collection on the field, on the set of all the atomorphism on the field F forms a group. Okay, any doubt?
No, sir.
So on the field of rational number and real number, we can define only one atomorphism. On the field of complex number, we can define two atomorphisms.
Two atoms.
ओके, तर असा पर्टिक्युलर दिला असेल तर किती करता येतील? जर दोन असतील तर चार, तीन असेल तर
Nine.
पहा, करून पहा किती फंक्शन्स एक्झिस्ट होतील. तसे 8 येतील कदाचित. ओके, एनी डाऊट अप टू हियर?
No, sir.
Okay, so today is sufficient. From tomorrow we see the third chapter, Galois theory. Okay, thank you for attending the lecture. You can leave now.